Having a good night's rest is important in maintaining a healthy lifestyle. Being able to track your sleep would give users more information on how to improve it. By recording and analyzing EEG, heartbeat, and movement data, we can give users deeper insights on their sleep. This can promote improved sleeping habits. We are the Dream Team, and our project involves the acquisition, processing, and the display of sleep data. The objective is to process this data into practical information that can be used to help improve the sleep quality of the user. Using the Muse device, we acquire the EEG data and transmit it as an EDF file through the Muse Direct cloud service. Heartbeat and motion data is acquired from a heartbeat sensor and an accelerometer. This data is then sent to a computer through an Arduino Nano. Using MATLAB, the EEG, heartbeat, and movement data is then processed to create a report on the night's sleep.
Right now we're looking at the GUI, which the user interfaces with in order to start signal acquisition and begin signal processing. First, the user will choose an appropriate COM port that is being used for serial communication. Once the user then clicks Start Acquisition, they will have 15 seconds to get into position and start recording their EEG. Recording the EEG is as easy as opening the Muse Direct app and clicking Begin Recording. This file is then automatically uploaded to their proprietary cloud service where it can be downloaded and accessed in the processing steps. The Arduino Nano sends information to the computer using serial communication. This is configured in the highlighted code. Here, we set the data rate in bits per second. This is called the baud rate of serial transmission. From here, we have a continuous loop which handles the sampling frequency for both sensors. The two logic statements are used simultaneously to check the amount of time since the last acquisition. We sampled the accelerometer once per second and the pulse sensor every 200 milliseconds in this case scenario. Here we track the time in milliseconds using millis, which is an Arduino function. After the appropriate delay is met, an integer value from the pin is read and printed to the serial port, along with text explaining which data type it is. This is how we're able to organize the data into two arrays once in MATLAB. When we click on the serial monitor and take a look at it, we can see what is actually being written to the serial port in real time. As you can see, the data comes through as an integer printed on the same line as the string data type as I mentioned prior. Also, it is clear to see that there are 5 pulse sensor samples for every accelerometer sample. So now we're looking at the MATLAB code, which is responsible for gathering serial data and organizing it into arrays based on the type of information. At the start of the program, we create and configure a serial port object and set the baud rate to the same as the Nano's code. With the serial port object open, we can now read the data that is being printed to the COM port. Next, we have a loop that runs for a preset period of time. This controls the length of the sleep test and is also used for organization of the two data types. When looping, the code fetches the most recent output line on the serial port and checks which string is included in it. This tag acts as the identifier and is removed before populating the data arrays. These arrays are then sent to be processed.
The data processing begins as soon as the Process Data button is pressed. By processing our 3 types of input, we are able to calculate the sleep state, heart rate, amount of movement, and body position of the user. We start by reading the EDF file, which contains 4 channels of EEG data that was just recorded using the Muse. We take the raw data from the channels and apply a bandpass filter to remove any unwanted frequencies. The data is then separated into 30-second epochs, and the power spectral density is calculated for each. A power spectral density, PSD, describes the distribution of power in the frequency components composing that signal. We then take the PSD and chop it up to give us the distribution of power for the brain waves delta, theta, alpha, beta, and gamma, which each have their own frequency range. Once these values are attained for each channel, we do an analysis and remove any channels that are deemed inaccurate. This was necessary because the muse does not always stay tight to the user when lying down, causing some channels to lose proper connection and give poor results. The total percents of each brain wave measured are determined and used to classify the sleep stage. Based on the percentages, we can classify the user's state as awake, drowsy, light sleep, or deep sleep for that epoch. In the accelerometer code, it takes the data that was collected in the acquire step and calculates the median angle of all the samples in that epoch. It then classifies each epoch as position left, right, or back. Looking at the same samples, we get the standard deviation in the epoch and classify the user movement as no movement, some movement, or lots of movement. The heart rate section scans through the data for each epoch, and every time the received value transitions past our threshold value, the heartbeat counter iterates by 1. Once we get to the end of the epoch, we divide it by the time interval and multiply by 60 to get beats per minute. Finally, the program exports all of the points of interest to a text file under today's date in the user's log.
Once the data has been captured for a given night of sleep, it's stored under their user profile in this log file here. Now what the user can do is they can log in to the interface here. They type in their username and password. If it's the incorrect password, they aren't able to continue and look at some of the statistics just yet until they type in the correct password. It will say login successful, and we can go to the statistics page here. So this page will go through the log file and present some interesting numbers and some facts about your sleep. It will tell you the percentage of time that you were in deep sleep or light sleep, which is also shown in this graph. It will calculate the min and max heart rate during the night and also show you it here in this graph. Down here, these are some interesting facts about your sleep. So this chart is a chart of how much movement you had while you were sleeping. So for this person, 90% of the time there was little movement or no movement, and only 5% of the time they were moving a lot. It will tell you the total number of hours of sleep, and also whether you slept mostly on your back, on your left side, or your right side. Additionally, the user can store a personal anecdote, which we can correlate with some of the data. So they can write, "I felt great when I woke up," and give themselves a score out of 10 and store that anecdote, which you can see is stored here along with the data. So finally, the user can go to the Insights page. This page will give you some more long-term data. So here we're looking at the previous week's data. It shows you how you felt when you woke up for the whole week and how many hours of sleep you got. And also some more interesting things such as throughout the week you moved very little when you were sleeping. You had a certain percentage of time in deep sleep, a certain percentage in light sleep, whether you predominantly slept on your right side, your left side, or your back. And also some interesting things such as when you had the most amount of sleep, you were sleeping on a certain side.